What if the moon was replaced with a black hole the same mass? This question comes from Sarah, who asks, if the moon were suddenly replaced with a black hole of exactly the same mass, what would actually change? Would Earth survive? Would we even notice? Great question, Sarah. The short answer is surprisingly little changes. And then, in one specific way, everything changes completely. The replacement. Let's be precise about what we're doing here. The moon has a mass of about 7.3 times 10 to the power of 22 kilograms. That's a large number. We're going to take all of that mass, compress it down until it collapses into a black hole, and place it at exactly the same distance from Earth, 384,400 kilometers away. Same mass, same position, same orbital velocity. The resulting black hole would have an event horizon, the point of no return, of approximately 0.1 millimeters in diameter, less than the width of a human hair. That's it. The most terrifying object in the universe, and it would be smaller than a grain of sand. You could not see it with the naked eye. You could not photograph it without knowing exactly where to point your telescope. It would be, for all practical purposes, invisible. What stays? Exactly the same. Here's the part that surprises everyone. Gravity doesn't care what shape something is. It doesn't care if the mass is spread across a 3,474-kilometer sphere of rock and dust, or compressed into a point smaller than a grain of sand. The gravitational effect on Earth would be identical. Completely mathematically identical. Earth would continue orbiting at exactly the same speed. The year would remain 365 days. Satellites would stay in their current orbits without adjustment. The International Space Station would notice nothing unusual. GPS systems would continue working perfectly. The tides would also remain exactly the same. Every coastal city on Earth, every beach, every harbor, every tidal ecosystem would experience the same daily tidal rhythm as before. High tide at the same time. Low tide at the same time. Surfers would not be inconvenienced in any way. If you went outside on a clear night and looked up at where the moon used to be, you would see nothing. Just stars. The night sky would suddenly be much darker. That would be the first thing people noticed. Not gravitational catastrophe, not the collapse of civilization, just a very dark night. What changes? Immediately. The psychological impact of losing the moon visually would be profound and immediate. Humans have navigated by the moon for hundreds of thousands of years. Calendars, religions, farming cycles, poetry. The moon is embedded so deeply in human culture that its sudden disappearance from the sky would trigger panic, unlike almost anything in recorded history. Emergency hotlines would be overwhelmed. Governments would issue statements. For the first 24 hours, the absence of a visible moon would be the dominant story on every news channel on Earth. Meanwhile, the black hole itself would be doing essentially nothing. It would orbit quietly, invisibly, exactly where the moon used to be. No accretion disk. There's no material nearby to form one. No radiation, no visible effect whatsoever. Just an invisible gravitational point patiently circling. The only way to detect it at all would be to look for the gravitational lensing effect, the way the black hole's gravity bends light from stars behind it, creating a subtle ring of distortion. With a very precise telescope pointed at exactly the right spot in space, you would see stars shift and warp slightly as the black hole passed in front of them. That would be your only visual confirmation it was there. The danger zone. Now here is where things get genuinely dangerous. The moon is approximately 384,400 kilometers away. At that distance, the black hole's gravity is no more threatening than the moon's. As we established, it's identical, but black holes have an event horizon. Cross it, and you do not come back. For our lunar mass black hole, that point of no return is 0.1 millimeters from the center. In practice, this means as long as nothing gets within a few kilometers of the black hole, nothing happens. The danger is not the black hole itself. The danger is anything that gets close to it. Any asteroid that was previously on a trajectory to hit the moon now has no solid surface to stop it. It passes through the space where the moon used to be, continues on its path, and keeps going. possibly toward Earth. The moon was quietly protecting us from some small impacts, simply by existing as a solid target. That protection is now gone. More significantly, any spacecraft sent to investigate would need to be extremely careful. Getting too close would mean death, not from radiation or fire, but from spaghettification, the process by which tidal forces near a black hole stretch an object into a long, thin strand of matter. At close range, the tidal difference between your feet and your head would be enough to pull you apart at the atomic level. You would become a very thin stream of particles spiraling inward. The eclipse problem. Here is the most visually dramatic change. Right now, once or twice a year, the moon passes between Earth and the sun, creating a solar eclipse. The moon's apparent size in our sky almost perfectly matches the sun's, one of the great cosmic coincidences. A total solar eclipse produces a breathtaking ring of fire, the corona, visible for a few minutes. With a black hole replacing the moon, the eclipse would look completely different. As the black hole passed in front of the sun, its event horizon, remember 0.1 millimeters across, would block essentially zero sunlight on its own. But its gravitational field would bend the sun's light around it in a perfect ring, a phenomenon called an Einstein ring. The sun would appear as a blazing circle of light with a dark point at its center, surrounded by a shimmering, distorted halo of bent photons. It would be the most beautiful and terrifying thing humans had ever seen in the sky. A perfect circle of fire with a void at its heart, lasting for several minutes. Every person on Earth positioned correctly would stop what they were doing and stare. Astronomers would weep. Photographers would not have enough memory cards. It would become the most photographed event in human history. Long term. Is Earth safe? Yes, completely. Over millions of years, the black hole would continue orbiting Earth. It would slowly accumulate a tiny amount of mass from interplanetary dust and the occasional small asteroid that wandered too close, but this would not meaningfully change its gravitational effect on Earth for billions of years. The real danger would come only if something large, another planet-sized object, passed close enough to destabilize the black hole's orbit. But this was true of the moon as well. A massive gravitational intruder would be catastrophic, regardless of whether our companion was made of rock or compressed into a singularity. In all other respects, Earth and its black hole moon would coexist in perfect, quiet stability. The final answer. So what actually changes if the moon becomes a black hole? Gravity, identical. Earth notices nothing. Tides, identical. Every beach, unchanged night sky. Completely dark. Moon visually gone. Lunar eclipses replaced by a haunting Einstein ring of bent light asteroid protection. Slightly reduced, no solid surface to absorb impacts danger to humans. Zero, unless you get within a few kilometers of it. Long-term Earth survival, completely fine. The universe does not rearrange itself dramatically just because we replaced one object with another of equal mass. Physics is consistent, patient, and largely indifferent to what shape its mass comes in. The moon is gone. Its gravity remains. And somewhere up there, smaller than a grain of sand, the most extreme object in physics is quietly doing its job. You just can't see it anymore.